Okay. So it's my pleasure to invite Krishna Hanumanthu once again to give his second talk on basics of algebraic geometry. So this is the fifth talk in the series, and I hope all of you have been doing your homeworks. Yeah. Okay, Krishna, go ahead, you can start.
Okay, thank you, KV. So I'll just continue from where I stopped last time, which was defining projective varieties or projective space. So let me just quickly recall the definition, then we'll continue. So I realized that many of the things that I wanted to sort of semi-formally define have been mentioned in the past lectures by Raghavan and Upendra. But anyway, this is it will be good to recall what they are. And I'll try to be a bit more, my purpose is only to give the definitions. They were using these things in their talk. So I hope to give you more details. And then we'll see. I'll see how much I can do regarding basics that I'm supposed to do. Okay, so I quickly will tell you again what projective space is. So n is, of course, an integer, positive integer. And we will look at Cn plus 1, remove the origin from it, and then we'll go modulo an equivalence relation. This is what I'll call Pn. And remember what the equivalence relation is. So we'll denote the tuples by A0 to An. So A0 to An is equivalent to B0 to Bn if, so this is the definition. If there exists a non-zero complex number, lambda, such that one is a scalar multiple of the other. The entire vector is a scalar multiple of the other. So this seems to be, the projective space seems to be the natural ambient space for many of the questions in complexity theory, where as far as I can understand. So this is important that you understand what this is. We've learned in detail what affine varieties are. These are closed subsets inside just the usual n-dimensional vector space. We will need to now consider closed subsets inside the projective space, as we are going to now define as a point set. This is what it is. So points of Pn will be denoted by something like this. We don't want to use the usual notation like this, because this would be a point in Cn plus 1, but it will only represent a class of a point in projective space. So we'll represent like this, and we will understand that one point can have different representations. For example, 1, 2 will be equal to, 3, 6 is equal to 2i, I being, imaginary. So this is not correct, of course. They're all same points inside P1. So we are basically going to look at lines through the origin. So these are lines through the origin in so each line in Cn plus 1, there's a bijective correspondence between that and Pn. Okay, so now the question is, we want to make sense of zeros of polynomials. And as I indicated last time, you have to be careful when you talk about zeros of polynomials or roots of polynomials, because you get into some obvious difficulties. So we want to talk about zeros of polynomials. Polynomials, of course, will be n plus 1 variable polynomials now, because you have n plus 1 tuple entries, points. So, but we cannot take, as I saw last time, we cannot take just any polynomial. So we can only consider, we first notice that we have to consider only homogeneous polynomials. Let me define these. And the reason, I will quickly recall the reason I gave you, maybe some example, maybe something like this. If you take this, and if you take P to be a point like 1, 2, this also, as I said, is equal to P 2, 4. So then what is f of P? If you use the first representation 1, 2, you get 1 minus 2. And if you use the second representation, you get 2 minus 4, or 2 square minus 4. Yeah. Right. So this is not a well-defined way of defining values. In fact, that we can never do, but we'll immediately see that we have to consider homogeneous polynomials. So you can define this any number of ways. A polynomial f in n plus 1 variables is homogeneous if every monomial in f has the same degree. So in the example that I wrote on the right here, that's not the case, because this monomial has degree 2, this monomial has degree 1, and that led to a problem. So we need all monomials to have same degree. So then we say that it is homogeneous. So obviously these are easy to see. I mean, this is homogeneous, whereas this is not homogeneous. Right? So the second one is not homogeneous because you see that the third monomial has degree 1 when the remaining two have degree 2. So now what can we do with homogeneous polynomials? The first point is, if f is homogeneous, then what we notice is f of a0 to an on the one hand, and f of lambda a0 to lambda an. Remember that these two are same points in the projective space. So we need f2, the value of f to be related. We don't quite get the equality. We will never get the equality. But because of homogeneity, we can pull out a, let's say, of degree d. Then we can pull out the dth power of the scalar here. So for all lambda in C. Okay, so lambda not equal to 0. So we can do this, right? But so we cannot even now have a unique value of f. So however, we can determine in a unique way whether f vanishes at that point or not. So f, whether f of p is 0 or f of p is non-zero, is well defined. Right? F of p is not well defined. The value of f at p is not well defined, but that's not required for us. We only need to know the 0 set. So all we need to know is that in an unambiguous way, we want to talk about whether something is vanishes at p or not. Okay, and that we can do. So now we can define. Now we'll just repeat the same recipe that we followed for the affine varieties. So now, definition, if you will, a projective algebraic set, or I'll just simply call it projective variety, is a subset, is a subset of Pn defined, which is the common set of zeros of a collection of homogeneous polynomials. So we cannot, for an arbitrary polynomial, we can't even define whether it is 0 or not in a well-defined way. But for a homogeneous polynomial, we can. So we can define a collection of homogeneous polynomial, and we will quickly get to ideals. So we have what are called called homogeneous ideals in the polynomial ring, and the projective varieties are going to be those which are 0 sets of homogeneous ideals, just as in the affine case. We have, okay, so I'll just quickly write this. I mean, this is, there is no need to repeat this process because it is fairly analogous to the previous thing. So remember, we had written a bijection between affine algebraic sets and radical ideals in the polynomial ring. So here, on the one hand, you have projective algebraic sets in Pn. And on the other side, you cannot put all radical ideals, but you have to put radical homogeneous ideals. In the polynomial ring over n+1 variables. Okay, so an ideal is homogeneous if it is generated by, so one can define this. This is an ideal. I inside this is homogeneous. I'll shorten it like this. If it is, so there are several equivalent ways of defining this, but one is this. If it has a generating set consisting of homogeneous polynomials. So for example, x1 square, x2. Remember, the generators may have different degrees. Is a homogeneous ideal. They need not all have same degree. So this is generated by this. These are all homogeneous. So it is a homogeneous ideal. Okay. So this is a by inclusion reversing bijection. So in other words, there is a version of Hilbert's Null-Stirling sets here, which says that if you look at the ideal, so homogeneous Hilbert's Null-Stirling sets says that if I is homogeneous, and you take first V of or Z of I by my notation earlier. I'm not intentionally writing all these things because they're very similar to the previous case. Z of I is the collection of all points on which I vanishes. I of Z of I is the ideal generated by homogeneous forms that vanish on Z of I. This is actually just nothing but the radical of I. So that gives you one of the compositions identity. The other one is easier. So this is what we have. Okay, though projective varieties are, I mean, they're defined in an analogous way. There are some concrete geometric differences between projective variety and geometric affine variety, as we'll see later. I mean, in the course of this talk. So I already defined. So projective variety is one, which is this common zero set of a collection of homogeneous polynomials. One useful way of one useful fact, let me say. So we can define, define UI to be all points inside projective space where the ith coordinate is non-zero. Okay, so UI is all points where the ith coordinate is non-zero. For example, so this is of course a subset of projective space. So example, U1 inside P1 will be A0, A1, A0, A1 is non-zero, right? And if you think about this, if A1 is non-zero, this implies I can write this because inside the projective space, I can always multiply a point by a non-zero scalar. I'll multiply by A1 inverse, which I'm allowed to do because A1 is non-zero. So this U1 actually happens to be A0 and 1, where A0 is now any complex number. And different complex numbers will give different points, right? So there is a bijection with C. So more generally, UI inside Pn is in bijection with Cn. Because in the ith coordinate, if you have a non-zero element, you divide by it. That sort of normalizes it. And then the remaining things you can't disturb anymore. Okay. So you do get the bijection with Cn.
There's a question.
Yeah, I
There is
just saw it.
Yeah.
Yeah, that is true. So it is a fact you can prove easily using algebra that if you have a radical ideal, sorry, if you have a homogeneous ideal, its radical is also the homogeneous ideal. I mean, it takes some work, but one can prove that. Yeah, so that's a good question because you have to stay in the realm of homogeneous ideals when you're talking about projective varieties. Okay, so you have this, and this, as we will see later, or we won't really prove this, but later I will assert after defining homomorphisms. This is actually an isomorphism of varieties. Okay, so this is what you have to think of. A projective space is a union of algebra geometrically. I mean, this is not just set theoretically or topologically, but in an algebraic geometry sense, projective variety space is a union of affine spaces, right? So because, okay, that I should have mentioned here. So we can easily see Pn is equal to U0 union U1 union Un. Because if you take an element of projective space, at least one coordinate has to be non-zero by the very definition. So it will be in one of them. Of course, there will be lots of intersections, but nevertheless, each of them is isomorphic to the affine n space. So for many of the local considerations that you will see in the course of lectures, it actually makes sense to study affine varieties. Because given any point in projective space, you can find an open set that contains that point and which is actually an affine space. Okay, so if you are familiar with manifolds or any kind of such notions, think of affine varieties as sort of building blocks of projective varieties or varieties in general. So everything is a union of affine varieties. Okay, so let me just, so most of the time I think in this course of lectures, you often will talk about either affine varieties. So a remark about varieties. So currently we have talked about only affine or projective varieties. So there is an adjective in front of variety. It's either an affine variety, in which case it is a closed subset of AN in the Zariski topology, or a projective variety, which means it's a closed subset of Pn, again in the Zariski topology, which I have not written here, right? This is clear. What is the Zariski topology on Pn? So just to record it here, Zariski topology on Pn is determined by closed sets or projective algebraic sets. Just like in the previous case, you can see that projective algebraic sets satisfy the axioms that one wants for closed sets in a topology. So they form a Zariski topology. So affine varieties are closed subsets of AN, projective varieties are closed subsets of Pn, but you still want to talk about what is called a variety without any adjective in front. There are a number of ways of defining this, but you do have to go beyond affine or projective varieties. And sort of the cleanest way of doing this, in some sense, that Hartshorne follows, is a variety is one of the following. Okay, so it's an affine variety. So let me write it here. So affine variety that means a closed subset. Remember in the Zariski topology, I'm not talking about Euclidean closed subsets in CN that are not in general, of course, affine varieties. Projective variety, so that is a closed subset again inside the Zariski topology, or in other words, common zeros of a collection of homogeneous polynomials. What is called a quasi-affine variety. So I will not worry too much about this. This is an open subset of an affine variety. And you also have quasi-projective variety. So this is an open subset of a projective variety. So in order to have any kind of interesting theory, whether you're talking about representation theory or algebraic groups or GITs, which you will learn in future classes, you cannot restrict your attention to these two categories. Okay, you will naturally have to, within your study, incorporate quasi-affine and quasi-projective varieties. But these four together will serve as good notion of variety for us. Though I will really not discuss too much about this. Okay, so for example, I mean, a really formal and precise way of defining these is as topological spaces with a with some notion of functions on them. So this I'll get to in a minute. But just to give you an idea, if you take an minus 0 for n greater than or equal to 2 is a variety in this sense, but it's neither an affine variety nor a projective variety. And one naturally has to consider this as a variety. So it's an open subset of an, so it is a variety in this more general sense, but not in this first two sense. Okay, so this is just a point that I wanted to sort of mention for future reference. Okay, so now as I said, a formal way of defining varieties is as a topological space attached with a valid notion of functions. So in order to do this, I want to talk about the notion of regular functions. And for simplicity, one I will stick to affine or projective varieties. Okay, so say X is an affine variety, and a regular function, and U is an open subset. So actually, I do consider quasi-affine here. So a function f from, so you want function means it takes values in the field, in our case, complex numbers, is so fix a subpoint in U. So a function is said to be regular if regular at P if there exist polynomials. So I'll not try this. So remember, if X is an affine variety, it by definition sits inside some AN, right? X is inside AN as a closed subset. So I have a priori fixed an N. So it is, these should be polynomials in N variables such that two things happen. G of P is, so sorry, I don't want F. I'll call F the regular function, G and H are my functions. I want H of P is non-zero and F is equal to, so by which I mean F of Q is actually yeah, so I should be careful here. So F should be defined by, so yeah, so it is a bit tricky. I have to So I'm sorry, I have to define it like this. So by which I mean, there must be a small neighborhood we have a topology in which there is a small neighborhood of P in U, such that H actually is defined by as a ratio of functions. So what you should keep in mind is that regular functions are ratios of polynomials. Okay, that is basically the summary of this. So regular functions are ratios of polynomials. Of course, in order for ratio of polynomial to be well defined, you want the denominator to not vanish at, so basically this is not enough. You want H of P to be non-zero in a neighborhood of P. So these are what are the regular functions. And now we say that these are the regular functions, notion of regular at a point. We say that f is regular on X, on U, all of U, if it is regular at all points in U. So at every point, there is a small neighborhood on which f is given by ratios of polynomials. So these ratios will differ from point to point, but at every point you have such a description. Okay, and one of the most important things that we will now define, I'll call this. This came up earlier. I mean, or at least indirectly came up earlier. So O of X to be global regular functions. So these are functions from X
Krishna,
to C.
Krishna.
Yeah.
So
Yes.
F is regular, F is H by G. I think somebody pointed out one silly mistake that you made.
Yeah, thank you.
Yeah.
Thank you. Yes, correct. F is the function and H and G are the polynomials. Yeah. So you want to take all of X and take functions which are regular at every point of X. So now if you think about this, what are the regular functions on all of the affine space? If you think about it, these are functions which have to be determined locally as ratios of polynomials. But if you take any polynomial of positive degree, it will have a 0 because you're in the complex numbers, which is an algebraically closed field. So you are looking at ratios of polynomials, but every non-constant polynomial has a 0, but at that 0, that function is not well defined. So it will be given by a different ratio, but then using some properties of the polynomial ring, you'll obtain a contradiction. So basically, what I just orally said is that functions which are regular on all of n is just the polynomial ring. So of course, every polynomial inside the polynomial ring will give a regular function, right? Via f by 1, because 1 never vanishes. So that's definitely regular at every point. But there are no other things. And this is easy to prove, but a little more work says that if X is an affine variety, what are the functions on X? Global functions. This is just, and we have already seen what it is. This is what we call the coordinate ring. Okay, this is the coordinate ring of, so this is of course, this is also a special case of this. So we have global regular functions are coordinate, just the coordinate ring of X. So now we have a similar definition for projective varieties, but crucial difference is, so maybe I'll not write the full thing, but this is important. So let me write at least the basic facts. So if X is a projective variety, so again, a closed subset, a regular function on, and here let's say U is open, on U, so a function, let's say a function f from U to C, P is in U, is regular at P if now, unlike in the previous case, when we wanted two polynomials, we of course want polynomials, but we don't, it's not enough that they're polynomials. They must be homogeneous polynomials. Not only are they homogeneous polynomials, but homogeneous polynomials of same degree. Let's say H and G and H as before, such that F is G by H locally. Okay. So by which I mean the previous statement that around a point of P, F is actually evaluated by computing both G of P divided by H of P. In particular, we want H to not vanish at P in a not just at P, but in a neighborhood of P. It's important that we take homogeneous of same degree for the same kind of issues that we encountered earlier, right? And remember, by the same degree, because if you now vary the point, P and P prime are the same points, that means it's lambda P. When you evaluate G of P prime, it will be lambda power D G of P, and H of P prime will be lambda power D H of P. So you cancel this. So you get the same value. So while evaluating a homogeneous polynomial at a point in the projective space is not well defined, evaluating a ratio of polynomials of same degree is well defined. So this is a well defined statement. And as before, we have what is called OX is regular functions at every point. And now this is an interesting, this is really the first, at least in the way I'm talking about it, the first fundamental difference between projective and affine varieties. In the affine variety case, there are lots of, think of it like this, there are lots of global regular functions, right? Because any element of this is a regular function on the affine space. And more generally, any element of the coordinate ring is a global regular function on X, any affine variety. That's not the case for projective varieties. Because what is O of Pn? If you think about it, these are supposed to be locally given by ratios of homogeneous polynomials of the same degree. But if you take a non-constant polynomial like before, which it must have a zero somewhere. So that will, earlier also we removed the possibility that denominator has to be 1, right? Only things that we consider are like this. But here there is no restriction on degrees. So you took all polynomials. But here we want homogeneous polynomials of same degree. If we are forced to have denominator of degree 0, we must have numerator also has to have degree 0. So actually, this is just constants. A constant is of course a regular function because it is given by ratio of two constants. And more generally, O of X is C. Okay, so here so here for these kind of statements you need irreducibility because otherwise you will have to have more copies of C. So I'm going to be a bit sloppy about such assumptions. So you have to take irreducible varieties for these statements. Okay, and a related remark which I should mention here is while we have a valid notion of coordinate ring of a affine variety. Okay, so maybe actually I'll postpone, so I'll try to remember this later because I want to make a few remarks, notions before that. So, and finally, I'll define now what is the meaning of a morphism. This was used by Raghavan Upendra several times, but I will nevertheless define it now. Let's say X and Y are varieties. You can think of them as this more general notion of variety. So they're either affine, projective, or they are quasi-affine or quasi-projective. A function, so let's say continuous function. Remember, they are topological spaces. So a continuous function makes sense. f from x to y is a morphism of varieties if for every, okay, so maybe I'll call this phi. If for every open set, I mean this, I'm just writing it so that you see it once. It's not important for the remainder of the lecture. For every open set V of y and a regular function f from V to C, the function f circle phi from phi inverse V, I mean restricted to phi inverse V to C is regular. So what you should remember is that it takes regular functions to regular functions. So you have V to C is regular. So if this is regular, this is regular. Okay. So morphisms are those which take pull back regular functions to regular functions. Okay, so there's some obvious, and once you have the notion of morphism of a variety, so you have already seen in previous lectures categorical notions. Once you have the notion of morphisms, you can have the notion, you can define the notion of isomorphism. X and Y are varieties. Let's say an isomorphism phi from X to Y is a morphism, and a bijective set map. So that inverse is also morphism. There exists a morphism psi from Y to X such that, okay, so let's see, to phi circle psi is identity on Y and psi circle phi is identity on X. Okay, so this is the case in any category. So if you have two objects, they're called isomorphic if there is a morphism in either direction, making two compositions identities. Okay, so and as an example, UI is isomorphic as a variety to AN, the UI that I defined earlier. UI is, you know, as above. Okay, so this is the collection of points in the projective space where the ith coordinate is non-zero. So some simple examples, and I'll try to connect some of the previous lectures to this. So let's say I have this. So P1 to P3. I'll define a point A comma B. So remember, P1 has two coordinates. It is C2 minus 0 modulo the equivalence relation. So I'll send this to A cubed, A square B, AB square, B cubed. Okay. It is easy to see that if one of we need to ensure every time you talk about projective spaces, you need to ensure that one of the coordinates is non-zero, because you are not allowed to have every coordinate 0. But if they're all 0, that in particular A cubed is 0, then A is 0. And if B cubed is 0, B is 0, which is not going to happen, right? So this being a point in projective line, you will have either A non-zero or B non-zero. So this is a well-defined map. And you can also see that if you send lambda A, lambda B, because these are all of the same degree, 3, it works out. That lambda cubed will come out. Okay, this is a well-defined set map. It's a well-defined set map. In fact, it is a continuous map. One can check this, because if you take an open set, that its complement is a closed set. So if you take a closed set, which is the 0 set of some polynomials, you can pull back and see that that's also 0 set of some polynomials. And more importantly, actually you can show that phi is a morphism. So if you take an open set of P3 and take a regular function and you take phi inverse u, it will, because of the, sort of loosely speaking, because of the way this function is defined using some kind of polynomial relations. When you pull back a ratio of polynomials, it will remain a ratio of polynomials. So it is a morphism.
So Krishna, roughly, I mean, if I write down a regular function there, it's at a point and it is the ratio of two things. You are basically going to substitute in that for every, if it was written as x0, x1, x2, x3, you're going to substitute x0 by a cube,
correct,
x1 by
correct,
a squared b, and so on, and then
correct,
take the ratios and finally show, right? That's
precisely. So if you take a ratio of polynomials like this, so by following Upendra's practice, I'll just say check this. I mean, check this. You have to check this to follow the, but as KV said, the basic idea is this. What is a regular function at the level of an open set in P3? So you can, for the purposes of this, you can restrict the open set further and think of this as some kind of a ratio. But when you pull it back, this is of course in P1. So this is phi, G circle phi. This is going to be defined by, so this is F circle phi. So this is F. This is going to be given by some, some suitable polynomials. I mean, you have to, G is a polynomial in 4 variables. So you have to take the appropriate relations coming from this function here. Okay, so this is also going to be given as a, okay, so that is the idea. Okay, so I wanted to just write some more. And in turn, when G is a group variety as Raghavan defined, so a variety which has group operations. So that means a map from G cross G to G, G to G, which is an inverse. All those are morphisms. So this is by definition. So I'm just repeating what he has. Okay, so this is encoded in the definition itself. So that's not really an example. But if you take GLN, see, this is an affine variety. It is actually an affine, algebraic group. Because it has the structure of an affine variety and it has the structure of a group with the group operations are algebraic morphisms. So that is part of an exercise, right? So check that. Group operations or morphisms. Again, loosely speaking, the idea is that when you multiply two matrices, you are only doing polynomial operations. So when you do that, when you pull back a polynomial function by this product map, you will get a polynomial map. So there's a question. So I think, it is not G. This pullback will be given by some. So you're right. So it's not just G because G is a polynomial in 4 variables. So it cannot be put here. So G tilde, H tilde will be polynomials, which will be suitably defined using this morphism. And the same happens here. So, and one can also remember now, G acts on Cn, let's say. This action is important for us. What is this operation? This is the usual thing, right? So you take A and a vector and you simply take it to right. And one can check that this is also, of course, this is required as part of a affine algebraic group acting on an affine variety. The action morphism, action map has to be a morphism. But again, I we'll let you check the details. If you take a regular function of some open set here, and you take the pullback, so let's say this is T, this map being essentially given by polynomial expressions will make the composition again a ratio of polynomials. Okay, so this is why this is a morphism. Yeah, so now I should sort of make some remarks which are special to algebraic, affine algebraic varieties. So some remarks. Affine varieties, not affine quasi-affine varieties. These are actually closed subsets of the projective space. Sorry, affine space. So let's see. Yeah, so if X and Y are affine varieties, so this is really a theorem, not just. X and Y are isomorphic if and only if the coordinate ring of X is isomorphic to coordinate ring of Y. So this is isomorphism as varieties. And this is isomorphism as C algebras or rings. Okay, so these are both rings over C. So the geometry is essentially encoded in algebra here. Okay, and this is of course not true. This is my earlier remark which I wanted to make. The above is not true for projective varieties. Above is not true for projective varieties. So the problem here is that there is, this is something I sort of tangentially commented on in the last lecture. I said that coordinate ring is an intrinsic object attached to an affine variety. So that is what this captures, right? The coordinate ring is an intrinsic object attached to an affine variety. Because if you have two affine varieties whose coordinate rings are isomorphic, those two affine varieties are equivalent or isomorphic, and conversely. So that is not the case for affine projective varieties. There is no intrinsic notion of coordinate ring for projective varieties. So there is only a notion which looks at the embedding, okay? But we have the following. Okay, so if we have X is a projective, so let projective variety, that means it is the zero set of a collection of homogeneous polynomials. We have homogeneous coordinate ring. So if you just follow the recipe that you used to define affine coordinate ring, you will get what is called homogeneous coordinate ring. So let me just use the same notation for this. Okay, so we have, if you follow the same recipe, you get what is called homogeneous coordinate ring. But this depends on the embedding. So if you put X inside some other projective space, you can in principle have a different coordinate ring. Okay, so I will give you a quick example for this. I must have written this somewhere. Okay, so as an example, you can take P1 map to P2. Okay, so it's similar to the earlier map I gave you. AB maps to, earlier I took all degree 3 forms. Now I'll take all degree 2 forms. So I believe these are important things that you should encounter. So this is what we call a 3-tuple embedding. So I think this kind of thing has already come up, right? We look at all forms of a fixed degree in a fixed number of variables. So here that's what we are doing. 2 variables, degree 3. There will be 4. So this is a degree 3, so 3-tuple embedding. You can have in general a d-tuple embedding. Here I'm talking about a 2-tuple embedding. So you can now think of a d-tuple embedding from P1 to PD, because there will be d+1 forms in 2 variables of degree d. So you can take that. So here, if you want phi2, phi2 is actually, this is not difficult to prove, is an isomorphism from to its image, of course. It's not a surjective map. Okay, so just to indicate to you how homogeneous coordinate rings are not intrinsic, I'm taken P1 and put it inside P2. So this is like a degree 2 curve in P2 actually. P1 sits inside a P2 as a conic. So now, given the embedding of P1 in P1 leads to homogeneous coordinate ring, because here P1 is defined by the 0 polynomial. So homogeneous coordinate ring is just Cx0, x1. Of course, this is an equality, but just to, so this is really X sitting inside P1, but X is isomorphic to P1 as varieties. But here, what is the homogeneous coordinate ring? It is now x0, x1, x2, because you take the 3-variable polynomial ring and go modulo I of x. And this you can actually check is C of x0, x1, x2 modulo x1, x0, x1 minus x2 minus x0, x1 square. So basically, remember, if you look at this, you want the product of the first and third coordinates is the square of the second coordinate. So here you have x1 square is x0, x1, x2. But these are not isomorphic. So the homogeneous coordinate ring has rings are different. Okay, so this is something I wanted to mention because unlike affine varieties, projective varieties have no intrinsic coordinate ring. However, when you're working with a fixed embedding, it is often convenient to talk about homogeneous coordinate ring. But you have to keep in mind that that is not a intrinsic object. If you change your embedding, this will change. Okay, so I have another 20 minutes or so. So I should, what I'm supposed to introduce to you also is the notion of, let's see. Okay, so I think I should quickly mention. Yeah, so I should mention, sorry. I should mention constructible sets. Okay, so this is nothing, I mean, this has appeared before. So I don't want to spend too much time on this, but so if X is a variety, a subset. So one question, so let me motivate it like this. If you have a morphism of varieties and you take a subvariety of the domain, its image is not in general a variety. So varieties don't go to varieties in under morphisms of varieties. So this is often an issue. that it's just a reality of life that image of varieties is not a variety. But you want to look at some nice sets, property of sets, which is preserved under images. And that's where a constructible set comes in. So a subset, I'm going to call it Y inside X, is constructible. Okay, so there are several ways of defining this. If, let's say, it is a finite union of what are called locally closed sets. And a locally closed set, okay, so I'll just write it like this. Locally closed implies open set union, open set intersection, closed set. So it's closed in it's open in its closure. So locally closed means it's the intersection of an open set and a closed set. And constructible set is a finite union of such sets. And the reason that we call these constructible is that, so constructible sets okay, so let's say the set of constructible sets inside X in X is the smallest subset of the power set, subset of the power set of X, namely the set of all subsets of X, containing open sets. Okay, so you can also start with closed sets. So let me close sets, subset containing closed sets, which is, it must be closed under finite unions and complements. Okay, so this is a sloppy way of writing it, but you start with the set of closed sets and you perform these operations and add more sets. You take finite unions and you take complements. So you immediately add all the open sets and you take finite unions and finite intersections because you take complements. So that new and bigger set is called constructible sets. So you can construct them essentially starting with varieties. So closed sets are varieties, so you can construct them. And constructible sets have this nice property, and this was mentioned at least once before, or maybe more than that. If F is a morphism of varieties, and let's say Z inside X is constructible, this implies F of Z is constructible. Okay. So this is important because constructible sets have this nice property that their images are also constructible. And the main example of this is, suppose G acts on X. G is an algebraic group and X is a variety. Think GLN and CN, for example. Then if you fix a point, we have the map we have this map. So image of this is exactly, of course, the orbit of X, right? And of course, G is a constructible subset of G, right? So this is a constructible subset of okay, this is an important theorem for future classes, that orbits are constructible. So they're, in particular, what you have is that they're, you can talk about their closures and they agree with the Euclidean closure. So this is, if you have a constructible set, whether you take Zariski closure or Euclidean closure, they agree. And to to prove some inequalities or non-containments. That seems to be an important requirement. Okay, so this was mentioned by Christian in his first lecture. So for constructible sets,
yeah, even Raghavan required reuse. No, sorry,
yeah,
Mukunda also used it.
yeah. So this came up in several of the previous lectures. The Euclidean closure. So because you have, if you are in CN, there is a Euclidean topology. Is the same as. See, Zariski closure is usually very big. It will contain Euclidean closure. But in the special case for constructible sets, they agree. Okay. Okay, so I have to now. So I wanted to talk about non-singularity and also indicate. I mean, this is something that I am not familiar with at all, but just to maybe anticipate what comes next, KV gave me some general information and I've looked up some things. So maybe I'll just try, I'm out of my depth here, but I'll try to sort of indicate roughly what people do and what I understand. So, and this is a notion of class variety. Okay, this I think was mentioned by Christian, but in a very simple case, I want to understand what this is. So let us do the following. Let's say y is a variable vector like this. So fix so we are going to fix let m be an integer and L is m square. And I'm also going to fix n. I think this is the notation that I'll follow. So I'll fix this and I'll call x. So sometimes I will think of this as a row vector, but sometimes I'll think of this as a m by n matrix also. It's a matrix because L is m square. I either think of it as an m square matrix, m by m matrix, or a row vector. Similarly, this is either an n by n matrix or a k vector. And I'll call x bar, just append y0 to this. Okay, so I have some obvious things here. So I'll define some vector spaces. So I'm going to take V to be sim my. This is a space of homogeneous forms of degree m in L variables. Okay, and similarly I have sim nx. So this is space of homogeneous forms of degree n in
squared.
Yeah, so this is so this is correct, right? Yeah, and in k variables. Yeah, so
in squared variables. Yeah,
n square variables. Yeah, so of course, if you take GL of so SL L of C, let's call this G, acts on V, right? Because V is an L tuple, you can multiply by L matrix. And similarly, let's see, so SL, okay, so SLKC acts on W. Okay, and we have a map. It's in fact an embedding. So if you are given a homogeneous M form by simply multiplying by y0 power n minus m, we get a homogeneous, it should be m minus n. m minus n form, right? So this gives you a homogeneous m minus n form. M minus n plus n. So this will be a homogeneous m form. Yeah. So is there some?
Your
Yeah,
m
so
is
there is
bigger.
something.
That's okay.
Correct. Actually, this L minus 1. So somebody suggested this. Yeah. Yeah, I should have L form. So yeah. So it should be L minus 1.
Yeah.
So this is okay, right? So these are
yeah.
degree m n forms. These are degree m forms. And m is bigger than n. Yeah. So this leads to, this induces a map from PW to PV, also an embedding, the projective space. Okay, so now this is where things get, I mean, I'm just going to sort of repeat what I've read. So if you take G to be determinant of Y, so at this point, I'm going to take Y as a matrix. This is an element of PV because determinant is a degree M form and I take its class, that will be in PV. Whereas if I take permanent of X, that's an element of this. Because that's an M, so this is like a minor in some corner, M degree N form. So, and then you have F to be. So it seems like these represent some kind of computational problem, determinant and permanent. So one can define, the class variety of let's say G or the determinant function is by definition closure of the orbit of G under SLC action. So you take the orbit of G and you take closure. That's called the class variety. So similarly, you have the class variety of, so this is denoted, let's say, by, and the geometric question that one wants to ask related to the complexity theory question, I'm sure this is all going to be explained, is whether we have a so basically what we want to ask is so essentially the problem is translated to a problem about inclusion of varieties. Okay, so this is going to be a constructible set. It's a closed subset, right? Because it's the closure of an orbit. And as I just remarked, this is a whether you take it as a Zariski closed or Euclidean closed, you get the same thing. So this is, I mean, when I go back and see Christian's first talk, at the end he was talking about such things. And now this becomes a purely geometric question where to prove such a non-inclusion, you have to essentially produce a point here which doesn't belong here. So you look at the ideal defining this and show that there is a point here where one of those elements does not vanish. Okay, so just to give you maybe a preview of what you want to do and why you want to do, I suppose, why algebraic geometry enters the picture. Okay, so I don't understand these things very well, but it looks like in the kind of questions that one studies in complexity theory, you have these analogs of these elements. One has to choose these elements carefully and look at their orbits and the closures of their orbits. Okay, so yeah, so I don't know the answer to Surijit's question.
Yeah, so no, we'll discuss this after you.
Yeah, because this is something that I looked at some paper of Mulmule and Milind. I just copied more or less from this. I wanted to isolate what the algebraic geometry part of it is. But I'm sure rest of the lecture series is going to be study of this. And my goal is basically to emphasize the geometry behind it. Can I take maybe 5 more minutes just to so that at least quickly give you the definition of singular varieties. So obviously
sure. This is a wonderful
singularities.
Yeah.
So let me just quickly, I wanted to, this is one of the topics that I should talk about. So I should not leave this to you, leave this without mentioning this. Okay, so before I talk about singularities, so if X is a variety, there is a notion of, this came up in previous talks, of dimension of X. So let me not write that yet. Dimension. So there is a way to define this topologically. This is like the largest length of the largest chain of irreducible closed subsets. Okay, so at this point, none of this really makes sense, but I'll write it just so that there is a record of this. Algebraically, you can define it using the notion of crude dimension of a ring. So these are sort of chains of prime ideals. But what you should really remember is dimension of AN and dimension of PN are 1. Okay, and also you have, if U is an open subset and X is irreducible, dimension of U is equal to dimension of X. Okay, and if you have
sorry, you mean N, no, there?
Yeah, thank you. Yeah, this is N, yes. And if you have the zero set of a single polynomial, whether it's inside AN or PN, dimension is 1. Okay, so these are some of the things that you should remember. I just defined it because it's important and it comes up in.
No, you mean again N minus 1, yeah?
Yeah. I don't know why I keep writing this. Yeah, I'm thinking of the ideal height. So yeah. So it's 1 less. So one equation means 1 less. 2 equations means it could be 1 less also. So it's at least N minus 2. So that is a bit tricky. Okay. So now I will first define it for affine varieties. That is the main thing to define. So suppose I of X is, some things like this, and let's say dimension of X is R, and this is some T. So you have an R dimensional affine subvariety of affine N space, whose ideal is generated by some polynomials. This T will have nothing to do with R. This T and R are unrelated most of the time. So you have what is called the Jacobian matrix. Which is simply the matrix of partial derivatives. So you have del F. Okay, so if this is AN has N variables, right? So this corresponding coordinate ring is C of X1 through Xn. You have those variables here. And you take partial derivatives of the generators of the ideal with respect to this. So now this is, of course, you have, it's either P by N or N by P, depending on how you write this. So now, P is said to be, so let's say P is a point in X. So X is, let me see how to define this, non-singular at P. So I'm sorry for taking more time. I'll finish in 2-3 minutes. X is non-singular at P if the Jacobian matrix evaluated at P. So here it's a matrix of polynomials, but after evaluating it becomes a matrix of complex numbers. You want this to have rank N minus R. Okay, so once you actually work out specific examples, it becomes clear. So very specific example is, suppose the ideal is generated by a single polynomial and the dimension of x is n minus 1. Then x is non-singular at P if the Jacobian matrix here is only one row but n columns. So you have, so I should not put commas. So this is like a row vector with n entries, has rank. Remember, the rank, desired rank is n minus r. Here it should be n minus 1, which is 1. So if you have a row vector, rank in being 1 means at least one of the elements should be non-singular, non-zero. So x is so therefore x is non-singular at P if and only if so this is what you normally mean by smooth point. You want at least one of the partial derivatives to not vanish.
High.
For some I here. So singular points are where all the partial derivatives vanish. So example 0, 0 is a singular point. Let's say, okay, so this is like a cuspidal curve and geometrically it looks like this. So if you take v of x1 square minus x2 cubed, partials are 2x and 3x square, which both vanish at 0, 0. And 0, 0 is of course a point on the curve itself. P must be also, f also must vanish at P. Okay, so let me just end with this might come up, I suppose. I mean, singular locus of x denoted by sing x is just the points where x is singular. X is singular means x is not non-singular. So it's either non-singular or singular. So, and this in our situation is a proper closed subset of so you can't have a variety which is singular everywhere. Okay, so in fact, in the Zariski topology, the singular locus is actually a small set. It's a proper closed set. So we often proper closed sets are considered small in Zariski topology. So you can have singular points, but they are actually not too many. In this curve, for example, the only singularity is this. Yeah. So in this entire curve, there's only one singularity. Of course, I should also add another example here, which is that z of, so z of, let's say y square x1 square minus x0 x2 is non-singular. So by non-singular variety, I mean non-singular everywhere. So this variety has, because if you take the derivatives, there'll be 2x1 and x and 1. So clearly they can't vanish because one of the derivatives is 1. So there can't be a point where the all derivatives vanish. So this is non-singular, which is to say that it is non-singular everywhere, whereas this is non-singular at every point other than 0, 0, but it is singular at 0, 0. And in general, non-singular singular locus is a proper closed set. So I think more or less I've said everything that I wanted to say.